Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to discuss instruction scheduling and all the related concepts that we need to use in order to schedule instructions from a compiler point of view, right? So let's read the question first. Answer the following questions given below. In assembly code snippet, assume that a single issue processor and the number of instruction cycles for load is 3, multiply is 4, and other instructions is 1. Then we are given some assembly level code, and then we are asked to calculate the minimum number of cycles required to execute the following program in its original instruction order using list. Then second part we have using list scheduling algorithm, perform instruction scheduling and compute the number of cycles taken to execute the program after instruction scheduling. So this is a pretty long question and we need to understand it step by step in order to get a good grasp of it. So first thing is assembly code. As you might know that in computer language we are given a high level language in which we write the code. Then we have the assembly level language, which is an intermediary in the computer system, and then we have the low level code. So the code we write is this, then it is translated to assembly level code, and from here it is translated to the low level language code. So that is assembly code. Okay, and assembly code is generally where we optimize the code. I would say that whenever we write a high level language, the compiler needs to optimize the code to improve the throughput of the system so that the least number of CPU cycles are utilized in order to execute the program. So just to make sure that the program which we write and the program which executes, the compiler tries to optimize it to improve the performance of the system. So that is what assembly code and its significance is. Now we move to the next part, which is a single issue processor, right? So a single issue processor we will discuss in the later part of this video. Just stick around for that. And number of instruction cycles is just clear knowledge, and I think rest of the terms is what we will discuss when we go further down in the video. So first thing is, like, we are given the number of cycles required for load and multiply, but we are given this fact that what is the cycles required for a load instruction and multiply instruction. For those who don't know this, load instruction is what we execute when we are trying to fetch a memory location, and the value stored in that memory location is being transferred into the register in a computer system. So that is load instruction, and multiply instruction is, I think you know that. So this is what we are given the cycles, but in general when we write a compiler, the code for a compiler, we don't know. We just take on some assumptions that okay, Intel based 64-bit architectures might be having like 10 cycles for a load instruction or something like this. So those are based on assumptions. So this is a typical example problem, so it is given here, otherwise it would be just based upon assumptions. Okay, now we try to understand what is this single issue processor. Single issue processor means any processor or CPU, as in common lay terms, that executes one instruction per cycle. We know that each CPU has a frequency of clock speed. So suppose your computer has 2.5 gigahertz as clock speed. So if it's a single issue processor, it will issue one instruction per cycle. So then it will be like basically only one thread or only one process will execute at a time. So that is single instruction per cycle, single issue processor. But generally today, these days, we are only having multi-core, multi-threaded processors which execute almost millions of instructions per cycle, right? So those are called multi-issue processor and will execute some n instructions per cycle. So that we covered. Now we come to the code part. So in the code there are many instructions, around like 7 instructions. So first we mark it or label it in the line numbers, so that we have ease while performing the rest of the instruction scheduling. So we just mark it with the numbers or alphabets in this example. So now we go down. So first thing which we need to understand is this: what is this load I? And then we have load. So what is these two? So load I is load immediate, and load immediate is used when we are trying to fetch a value, a constant, right, and storing it in the register. So suppose we, in this example, we have 5 and we are storing 5 into R1, which is a physical register. So that is load immediate. But just in the next line we have load X into R2. So X is a memory location. It's not a constant or a literal value, right? It's a memory location and it can hold any value. So first the system needs to go to that memory location, and once it finds the value in that, it then needs to fetch it inside the register. So that is load statement. So after that what we have, so this we understood what is the difference between load immediate and load. Then we have the role of instruction scheduling. So why are we doing basically this? Instruction scheduling is what helps the compiler to minimize the number of cycles required to execute a code, right? If instruction scheduling would not have been there, then it might be possible that the code written by the programmer is too slow or too inefficient to be run by the processor, and it may take longer. And if the code is quite large in size, then it might also happen that the code may crash the system. So in order to minimize the number of cycles required to execute a code, we have instruction scheduling. Not only that, we have another important factor which is handled by instruction scheduling is register pressure. Register pressure technically means the number of simultaneously live variables at an instruction. But let me tell you that the technical term might be quite daunting for someone to understand, but this is basically what we have discussed in some of the previous videos you might find in the channel, is the code optimization part. So in code optimization we have seen that when we are trying to pull a variable from memory to register, we have a term known as spill cost, right? So this spill cost is a bit of like overhead for the computer system, and because of this, the time which is going in doing this transfer from memory to register and this register from memory, so this is taking extra time for the code to run. So that increases register pressure. So that is what I have written, that basically it's the case when more spills or reloads are needed to execute the program. So I'll mark some videos in the I button here, so that you may go through them as well, so understand this concept specifically if you want to, and I hope that will make sense. Okay, now we come to the next part, which is we need to estimate the number of cycles required to execute the stream of instructions, right? So just what we will use in this part is the information we are given here, like load requires 3 cycles, multiply requires 4 cycles, and other instructions require 1 cycle each. So in our case, the first instruction is load immediate, so it will require 1 cycle. Then we have load X, which requires 3 cycles. Then we have other instructions, which is basically add. Suppose let's take an example of add R1 and R2, and it will go to R3, register R3. So why do you think that it takes 1 cycle? I need you guys to just think upon it and write your answers in the comment section if possible. So this is because registers are basically the most fastest storage system in a computer architecture, right? So each operation in that takes only one cycle. Each operation in a register, that is if we want to add it or subtract it, or whichever operation is possible in the register, if we do that, it will just take one cycle of the CPU. So that is why this is 1, and your register operations take unit time, right? So this is what we have, and we need to remember that load I is not equal to load. This is a common mistake which people do. So then we have, like, this is what we will do for the all the instructions to estimate their number of cycles required. Okay, this is what the compiler as well does, although it does not have the exact information according to the system. Based upon its assumption, it just tries to calculate the number of cycles it will require. Perfect. Now we come to the next part, which is the data dependency graph. Data dependency graph is something which helps us find which variable we need to first calculate in order to proceed in the execution of the program. There are, like, when we write the code, we know that there are some variables in the code which need to derive their values from the variables mentioned above, right? So we cannot just go down and try to fetch those variables before defining the previous variables. So this is the case when we are dealing with code also. So we need to find some variables before we go down and try to execute other statements. So this is what is dealt in data dependency graph. So in data dependency graph, what we will do is we will just assign the cycles that are needed to the various statements, which are basically marked above in here, right, A to G, and according to their whether it's a load instruction or a multiply instruction or whatever, we will just assign the numbers based upon that. So here, since A was a load immediate statement, so its value is 1, then we have load, so its value is 3, and similarly all of them are basically marked. And now you can see that these arrows basically indicate the direction of the flow, right? So first we need to define A, we need to define B, then only we can obtain the value of C, or we can execute the statement C. So this is the dependency. When we have to find the dependency, so here C has dependency 2 because it depends upon 2 statements. Similarly, if we come to F, we see that D isn't dependent on anyone, neither is E dependent on anyone, right? But F is dependent on both D and E, right? So its dependency is 2. Now if we just go down, we will see that G is executing. So G is also dependent on 2 variables, C and F. Mind it that we will not say that it is also dependent on A, B, D and E. No. What we will say is just that it is directly dependent on C and F, so its dependency is 2. So I hope this makes sense. Now we'll just proceed further. So what was the first question we were asked? So the first question is, calculate the number of minimum cycles required to execute the following program in its original instruction order. It means that we don't need to optimize it as of now, but we just need to find the minimum number of cycles that will be required to execute this code, right? So that we will do. Minimum number here just means that according to dependency graph, we will just calculate that, right? So first we can either choose any one of these, like A, B, D or E. So we will choose A, or better, that since we are trying to find the minimum possible number of cycles, what we can do is just choose A or D, because you can see that there is only one cycle required by A or D, because these are load immediate statements. So to minimize the number of cycles, we will do it in ascending order, right? Then what we do is, then we find the value of B, right? We execute the B statement, 1 and then 3. Then since B takes 3 cycles to execute. So the next 2 cycles will be stall. Stall means no instruction, new instruction will execute during this time, because we have a single issue processor. So this particular instance, the no new instruction will be executed basically. Same is the case with 4. These are basically, you can mark it as timestamp, I would say, or cycle number, but this is how it works. So we are stalling the system in these 2 cycles. Once it is done, then we will execute C. Now since the dependency of C has become 0, right, both the variables on which it was dependent, they have been executed, and now it's available to be used. So now we execute C. C, as you can see, that it is only like 1 cycle it takes to execute, so it will execute in a while, and then we will go to D. You can see that we cannot directly execute F because it has dependency 2, so we will just go to D. Again we will execute it in 1 cycle, then we will go to E. So then we go to E. Again it stalls for 2 cycles, because in total these are 3 cycles. So once that is done, again dependency of F becomes 0, and then we need to stall, because F has F has the number of cycles 4, right? So we will stall for 3 more cycles. So this becomes 4, right? Once that is done, then we go to execute G, and G will be executed because its dependency will become 0. So that is the first part of the question. I hope this is clear, right? So then we need to calculate the total number of cycles which we took. So since we kept a count of that, so it's just 14. So I hope this makes sense. Now we move to the next part of the problem. Let's go and check what was that. This is using list scheduling approach, perform instruction scheduling and compute the number of cycles taken to execute the program after instruction scheduling. So just we'll have the look on how we will do that. So list scheduling, as the name suggests, is a scheduling algorithm that is based upon some lists, right? We need to have some predefined lists based on some data that I will discuss, and based upon those lists we will decide which instruction to be scheduled first or prior than above others, and which instructions can be scheduled on a later part. So the first thing which we require is the ready list, and the second thing which we require is the critical path distance with respect to every instruction. So if you are not familiar with these two terms, no issues, I will discuss them in detail, so just stick around. First thing is the ready list, right? So before I discuss what is ready list, I want you guys to just pause the video and try to think that what could be a possible gesture of ready list. Try to relate it to operating systems you have gone through, if you have gone through a course on it. So I'll just discuss it. So ready list is those instructions whose dependencies have already been completed. So if suppose we have A, right? So its dependency is already 0. So it can be put into the ready list. But in the beginning, C has dependency 2. So it cannot be put into the ready list, right? Because it has dependencies that are not yet completed. So this cannot be put into the ready list. Perfect. Now we have understood what is ready list and how we need to basically populate that. Now we come to the next part, that is critical path. Critical path is somewhat, you can say that it is the steps that we will take in order to reach to the final destination from a given instruction. It will make more sense when I go in the definition. So it is the longest path between this instruction and the leaf instruction in the data dependency graph. So technical terms are quite bit daunting, I know, but if we go in a bit detail, we will see that the longest path, it says the longest path, means from a given node, the instruction between this instruction, that is the node itself, and the leaf instruction. The leaf is the last instruction of the, suppose this is the dependency graph, and right, this is the dependency graph. Okay, so from this, let me change the pen color. From here, suppose this is the starting point, so we need to find out the distance from point number 1 to point number 2. This is the leaf instruction in the data dependency graph. This is the leaf. Although it might seem that this is an inverted tree if you come from a computer science background, but I would say that this is the leaf. Just to remember this, this is the leaf of the data dependency graph, and this is the starting point, I would say. So I hope critical path distance is clear right now. So we'll move to the next part. We need to calculate this critical path distance for every instruction, right? So for every instruction, if we see that we can calculate like this. Let me just go back to the data dependency graph. Suppose we are in D. So the longest path from here to here, what can it be? So it's basically 1 plus 4, right? There is no other path, so it's 1 plus 4. Similarly from E, it will be here, so it will be 3 plus 4, 3 plus 4. Similarly for B, it will be 3 plus 1, and for A finally it will be 1 and 1, so 1 plus 1. So this is how we calculate the critical path distance for all the instructions. And if you are wondering what it will be for G, so it will be 0, because it's on the leaf node itself, so there will be no critical path distance associated to that. So we have now calculated the critical path distance for all the instructions basically. I hope G is not written, so it's 0. So in this, what we need to consider is which is the largest, because the largest CPD sort of tells us that what could be the number of maximum cycles that will be required. It just gives a lower cap, you can say that if the number of cycles, let's say max and min. So this most critical CPD will give this minimum value. So we can say that at least 7 cycles will be required to execute all these instructions, right? Because it is the most critical instruction out of all these instructions. Okay, so now we found that how can we basically get a cap or a lower cap on the minimum number of cycles that we require. Obviously we will require more than this because there are more instructions and stuff, but minimum can never be less than 7, right? Now we come to the next part. Now we are finally ready to basically start list scheduling. So list scheduling will have some format, you can say. So in the format, the first thing is cycle number, right? We need to determine which cycle number we are currently at. Then we have the ready list, right? Then we have the instructions chosen, which instruction we have currently chosen. Then we have the active list, and I will share some remarks based on what we do, so that I will discuss in a while. So first thing is the cycle number. In first cycle, we have 4 items in the ready list, that are A, B, D and E. So these A, B, D and E can be written directly because all these have dependency equal to 0. Only those who have dependency equal to 0 will be put into ready list at any particular given cycle. Then we need to choose a instruction. So how we will choose the instruction basically? Instruction choosing is very important when it comes to list scheduling, and it will only be chosen with the value of highest CPD. I want you guys to pay close attention here, because this is important. This is important. Let me change my ink. We need to use the highest CPD in order to choose the instruction. Just because we need to find the value of the instruction that will take the longest time to execute. So once we have chosen the instruction, we'll put it into active list. Active list is what? The processes or the instructions which are currently executing. So those are in active list. So what we have done is just chosen E because it has highest CPD, and E will execute for 3 cycles, which we have the information basically from previous knowledge. Right, now we come to the next cycle. So since E was already sent into the active list, so it will get removed from here, and now we have 3 instructions. Why 3? Because only 3 instructions as of now have dependency 0. So now we choose the next highest CPD, which is D. As you can see, the next highest CPD was D, which is 5. So we choose D. We will move it into the active list, and you see that we have E as well D. This is because E is still executing. You remember that E will take 3 cycles to execute, so it will go for 3 cycles here before it finishes off. So that is why it is still here in the active list, and we will just add D to it. Perfect. Now we have just D gets added, that is the remark. And now we will get to the third cycle, which is A and B. Now D goes away, so we have B now. B is next in line with the dependency CPD, so B will have that, and D will execute in 1 cycle itself, so then we will be having B. So E will be completed in this term, and from next cycle we will have cycle number 4. So in cycle number 4, F will come, because we have executed we have executed E, we have executed D, we are executing B, and now we can execute F because the dependency has converted into 0, because E and D are already executed. So since E and D are already executed, we'll just have F into the ready list. Instruction chosen will be F, and because it is like higher than A in CPD, and we'll have F and B because E has already got completed, and we will have, so F dependency turned to 0. Right, now we come to the next. We have only A left. Why A? Because C is not yet completed, because B is not yet completed and A is not yet completed, so C cannot be pushed into the ready list. So we will execute A, and we will have A in the ready list. Remember that we need to keep the cycle count in mind so that each instruction executes in its time. So like E executed for 3 cycles, B executed for 3 cycles, now F will execute for 3 cycles. But those instructions which will be only executing once or in 1 cycle will have only, like A executes here, so it will not be repeated in the next line. So that's how we will execute these, and once we see that B is done, A is done, now we can push C into the ready list, and C is only there, so it will be pushed into C, into the instruction chosen. Then we have C here, and since F will take 4 times, so it's 4 times written here. So then we have C completed, and in the 7th cycle we have nothing. So why this occurred? Because G has still dependency 1, because F is not completed. So G has to still wait in order to execute because F is not completed. So there will be nothing in the instruction chosen, and we'll execute F in the active list. Once F has finally done, then we have like G in the instruction chosen, G will execute, and we are done with the instructions. So we see that we have taken 8 cycles. As we saw previously that minimum it will be 7, right? we will obviously take more cycles because there are other instructions as well, and we need to optimize this in a way using these lists, ready list, instruction chosen, and active list, in order that we can just reduce the number of cycles. As you might remember that when we are doing the first part, it took us around 14 cycles, right? So almost like it almost reduced to half, I guess, if not less. It almost reduced to half because 14 cycles it was executing in the original order of instructions, but when we have in the list scheduling approach, then we can execute this in only 8 cycles. So this provides great optimization to the computer side, and this is how we are able to execute so fast in the compilers or the languages which are like C++, Java. These can execute so fast. So in the dependency count, we just need to keep in mind that as soon as like A and B, one of them gets over, so we'll have 1 in C because only 1 is left, then 0. So we just need to keep this count in order to like insert new instructions into the ready list. So that will be done, and just as the dependency count becomes 0, we'll just move them into the ready list. So that was it. I hope I was able to make you understand the instruction scheduling and how it optimizes the performance of a compiler and why we need instruction scheduling basically. And if you still have any doubts, then feel free to reach out in the comment section below. And that's been it. Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.